Hello, welcome everybody. Can you hear me?
Yes, sir. Yes, sir. You're audible.
Yes.
You're audible.
Very good. So welcome everybody to our IEEE Signal Processing Society Seasonal School on Networked Federated Learning, Theory, Algorithms, and Applications. I'm Alex Jung. I will talk a bit more about myself in a second and also about the school organization. But first, let me point out the organizers of the seasonal school. So this school is under the auspices of myself. I'm representing the IEEE Finland chapter on signal processing and circuit analysis. We are also having the IEEE Finland chapter on automation, represented by Professor Simo Serke, which will also give a lecture, I think on Wednesday. And we will have, as organizer, the IEEE Vidzak Bay chapter, represented by Dr. Murthy. Murthy, are you here? Would you like to introduce yourself with a few words?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yeah, thank you, Alex, for your nice introduction. So this is TSN Murthy, working as a assistant professor in the Department of EC, University College of Engineering, Jawaharlal Nehru Technological University, Kakinada. So I'm working in southern part of India. Coming to our chapter, I'm as a chair, Communication Signal Processing Society Joint Chapter, IEEE Vizag Bay section. Section was started in 2020. From the last 2 years, we are organizing many technical events and workshops, particularly with the support of support and a lot of help also received from Alex Zeng. We organized one seasonal school in the month of September that got a lot of big success. And this is the second school completely. Alex supported me to organize this event. Definitely, we would like to continue same kind of relationship in future also to do some good and quality access for the benefit of the IEEE members. Thank you very much, sir. Alex, this is from my side. Yeah.
Thanks a lot. I really appreciate here this cooperation of parts from different parts of the world, which is very much needed at the moment. And IEEE is an excellent venue to have such international collaboration and working together.
Yeah, thank you.
This seasonal school. So just to point out, this seasonal school is also offered as an auto course, so you can earn 2 credits. It goes under the name Special Course in Machine Learning and Data Science. Though if you're interested in this and if you're a student at the Finnish University, you find more information about this on the My Courses pages of Aalto University. The exam will be based on a discussion of the exercises. So today I will spend most of the time of this lecture on discussing the exercises and the content of the exercises, and they will be the subject for the examination. Okay, a few words about me. My name is Alexander Jung. I graduated in 2012 from Technical University Vienna. So I did my undergraduate and graduate studies in electrical engineering and signal processing. So depending on the audience, I call myself a signal processing scientist and engineer, or a machine learning scientist and engineer, whatever is more useful for me. And since 2015, I'm assistant professor for machine learning at Aalto, where I lead the group Machine Learning for Big Data. I'm associate editor for the IEEE Signal Processing Letter since 2020. And I have been active as chair of the IEEE Finland chapter on signal processing and circuit and systems. And my tenure here will end this year. And I would also like to use this opportunity to point out, if you're interested in taking on a role, becoming chair or co-chair or other role in the board of this chapter, for example, organizing such events, please drop me a line. So we will soon have a call for nominations, but if you're already now thinking about it, I would be happy to discuss this with you. Just a quick overview of what we do in our research. Our research has currently 2 main threads. One main thread is the subject of the seasonal school, network federated learning. So I will talk a lot about this subject during the next hour or so. So I will not spend too much time. Just to point out, also we have another recent research agenda, research avenue, which is on explainable machine learning. So we also study how to provide not only highly accurate predictions, which will be the main subject of this school and this lecture today, but also we study how to compute explanations and how to quantify the quality of explanations. Okay, that was my quick background overview. So now about the school. The school format is as follows. We will have lectures like the one today, which will be offered via Zoom that we currently have here. We will record the lectures, so we will record all the lectures, but don't worry if you kind of appear in one of the recordings, we will always ask you before publishing anything with your voice or face on it. So don't worry about this. We will be very careful with publishing these recorded lectures. But so you know, if you cannot make it to the lectures, we will provide the recordings throughout the course, throughout the school. Then we will have exercises. These exercises will be based on Python notebooks. So we'll show a bit more about Python notebooks later in this lecture. But this is mainly independent work. So we think that the best way to learn is by doing. So you should work through these notebooks yourself. These notebooks contain demos, so ready-made code snippets that you just run. So a first challenge might be how to get a Python notebook environment running. And for this, I just want to point out, we have at our school site, which will be a main communication channel, the school site. So you be sure you can access the school site and you know the web address. So two-step verification. So we have on this web page, I have put a link to some instructions that one of our teaching assistants, Dr. Yu Tian, provided. And here you find step-by-step instructions how to set up, as I understood, this is kind of a virtual environment or a virtual machine using this Docker software or Docker application. So then you should be able to run the notebooks without any headache. Yeah, and this already brings me to the next main component of our course. If you have problems to get this running, to get these Python notebooks running, don't hesitate to ask questions and also to answer questions on our Slack channel. So we have a Slack discussion forum, which also is organized into channels. So we have a channel for exercise 1, a channel for exercise 2, and a channel for exercise 3. So if you have questions regarding exercise 1, then I encourage you to put your question there in the channel for exercise 1. And also I encourage you to answer questions of others. So if you answer questions of others in this discussion forum, this might not be at your disadvantage should you want to complete the course or the school as an alto course and want to get credits. So we will take this active participation also in the discussion forum into account. Okay, yeah, and also please do not hesitate to post any questions here on the chat in Zoom. I try to answer questions regularly during breaks. Okay, yeah, now one of the main components of this school are the lectures. We will have a series of high quality lectures. I quickly go over this list of lectures. We will have tomorrow the lecture on basics of spectrograph theory by Professor Avrachenkov from INRIA, France. On Wednesday at 10, so all these times are Eastern European summertime. So this should be EEST, which is the local time in Helsinki. And Wednesday at 10, we have the lecture on parallel and distributed methods for state space models by Professor Simoseke. On Wednesday, we have on 12:30 a lecture by Dr. Hamid Tavakoli on compact and efficient neural networks, steps towards communication efficient federated learning. On Thursday, we will have a lecture by Dr. Irene Schicker from the Austrian Meteorological Institute about machine learning applications in meteorological forecasting, which is highly topical because you might need to predict how much solar energy and how much wind energy you can harvest in the next 2 or 3 days. Then on Thursday, we will have a lecture by Dr. Samek from the Heinrich Hertz Institute in Germany about towards communication efficient and personalized federated learning, followed by another lecture on a similar topic, communication and computation efficient distributed machine learning by Professor Carlo Fischione from KTH Stockholm. And on Friday, we will have a lecture by Diplom Engineer Saranti from Austria, Technical University Graz, on tackling the problem of bad explanation with in the human in the loop principle. Yeah, you can find abstracts for all these lectures on the course page, the link of which is shown here again. So on this course page, you can find abstracts to all the lectures. But as I pointed out, let me repeat again, all lectures will be recorded and made available on the school site. Okay, yeah, and also if you have not already joined this discussion forum or Slack, please do so by today. This might be really helpful for you to work through the exercises. And we will have amazing support for you. So I'm very happy that I got the confirmation from 3 excellent teachers that help you with getting started in these notebooks and with Python. We have Dr. Yutian, Dr. Shamsiat or Shamsi Abdurrahmanova, and Master of Science Dick Carrillo Melgarejo, helping you with your questions and problems in the exercises. Okay, so now the main part of this lecture today is about the exercises and the contents of the exercises. We will have 3 exercises, exercise 1, 2, and 3, and each exercise consists of a Python notebook. So you should, ideally, you should have some basic experience in running a Python notebook. Otherwise, I would expect you to try to get started with it by today or tomorrow. So this is really the minimum requirement, that you get an environment where you can open Python notebooks, run them, execute them, and edit them. Okay. Yeah, each notebook. Yeah, by the way, these notebooks are already available at the course site. So let me show this to you. On the course site, you can download the notebook for the exercises. So if I click it here, yeah, download starts. And then you get, in your download folder, you get the notebook, which has file extension IPYNB, Interactive Python Notebook. Or something. Okay, so the notebooks for the exercises are already on the school site. Feel free to download it, to play around, get a feel for it, and ask questions on the Slack discussion forum. But I will now try in this lecture give you an overview or the background for these exercises. So these exercises are inspired by a toy application, which I use in most of my machine learning teaching. And this application is a rather innocent application. It's about the weather. So the problem that I have in mind, or the problem that I'm facing often now, still now in Helsinki, we still have snow. So you wake up in the morning and what you can measure about the day ahead is the minimum temperature, because this is typically something you get in the morning. In the morning, you measure the minimum daytime temperature. And nowadays, you don't measure it by a thermometer outside your window, but you Google it. So you don't need any thermometer anymore, but the morning temperature is something I can measure easily. What I cannot measure easily is the maximum daytime temperature. Will it be +5 at the mid of the day, or will it be -5? And based on this quantity of interest, or we call this label, so the label of a day is the maximum daytime temperature, I choose different waxing for my skis and also different clothing. So the problem here is to predict the maximum daytime temperature based on the minimum daytime temperature. And in exercise 1, I want to get you on speed to show you how to learn such a predictor, how to learn such a map. We call this a hypothesis map, which reads in the feature, the property of a day that I can measure easily, which is the morning temperature, and outputs a prediction for the quantity of interest, which is the maximum daytime temperature. And you will learn in exercise 1 how to do this using the principle of empirical risk minimization. And in particular, you will learn how to solve this empirical risk minimization problem using gradient descent. And this gradient descent will also be our algorithmic tool for basically all other exercises. So everything we do in this school, you can understand as a specific instance of gradient descent. All the algorithms you learn in this school essentially are instances of gradient descent. Okay, exercise 1 will teach you how to learn such a predictor for the maximum daytime temperature based on data. So you will also learn how to read in data points from a CSV file. And for this, we will use the Python package pandas or Python library pandas. So you will get familiar with, you will learn how to use pandas functions to read in data from a CSV file. And our second main library in exercise 1 is NumPy. So NumPy provides techniques for working with numeric arrays. So did any one of you ever work with numeric arrays? Does any one of you know examples of numeric arrays? Yeah, feel free to text something on the chat. Yes, matrices. Hello. Matrices are numeric arrays. Vectors, feature vectors, these are all numeric arrays. So NumPy is their tool in Python to work with numeric arrays or tensors, yes, higher dimensional numeric arrays. A regular arrangement of numbers is a numeric array. A vector is a one-dimensional array, matrix is a two-dimensional array, then we can have a tensor with more than 2 dimensions. Okay, so this exercise 1 shows you how machine learning consists of 3 components and combinations of 3 components. So we have data. You will see how to get data in the form of data points. You will use a specific model in exercise 1, which is a linear model. A linear model consists of all possible linear maps. It's a very simple, but I would say that still the most widely used model in machine learning. Then you will see how to choose or how to train a model using the notion of a loss function. In particular, we will focus on the squared error loss, which is the first choice or might be a popular choice if you want to predict numeric quantities. Like in our case, we predict the maximum daytime temperature, which is something numeric. Okay, so let's start with data. So in exercise 1, you will see how to read in data from a CSV file using a few lines of Python code. In particular, there's this function read_CSV, which reads in data points from a CSV file into a Python object called df, whose type is data frame. So we call this a data frame in Python. And it's basically a data frame is a Python object that carries a data set. A data set is a collection or typically a sequenced or an indexed list of data points. So we have some index. We have the first data point. In Python, we typically start counting with 0. So this is something you might remember at times. So we start counting with 0 in Python. In mathematics, in textbooks, it's often the case that we start counting with 1. So the first data point is 1. However, in Python, typically the first data point in a data frame is index 0. Okay, and then we see in each row here 1 data point. So 1 data point here could represent one daily temperature measurement somewhere in Finland. So 1 data point represents 1 daily weather measurement. And then each data point has certain properties, like these are the columns. The property could be here the date, when did this measurement have been taken, or when has this measurement been taken? Then also the station. So we can take, at the same day, we can take different weather measurements at different locations. This is another property. Then we have the minimum temperature during the day that has been observed in this measurement, and the maximum daytime temperature. So, as I said, in our toy application, the minimum temperature is what we consider as a feature. This is something we measure in the morning. We assume we can measure it every day, also today. However, the maximum temperature is something we cannot always measure, in particular not today, because it's ahead of us. We need to predict it into the future. But how can we learn to predict? How can we learn to predict the maximum daytime temperature from the minimum daytime temperature? Well, we need to learn some map, which we call a hypothesis, that reads in the feature and outputs not the label. Typically, we will not be able to perfectly predict, but we will get an approximation or an estimate for the label. We call this a prediction. And in particular, now in exercise 1, we will use a linear model. So a linear model is, strictly speaking, the set of all linear maps. So the set of all maps that take the input features, and these features are typically in a numeric array or vector. So we have more than one feature. So this X here is actually a feature vector. So we have feature 1, X1, and feature 2, X2. These are two features of a data point. But here we plot this map only as a function of X1. So each of these curves corresponds to a specific choice for X2. And in the exercises, we will use a very somewhat stupid choice for a feature, which is always equal to 1. Yeah, there's one comment. Is there a problem with the streaming? Can you hear me and see my slides properly? Yes, so there seems to be many participants get the stream nicely. So I'm sorry if some of you have problems, but I guess we have participants from all over the world. So sorry for that for some of you have connectivity problems. Okay, I hope, yeah, but the recording will be put online and this should be fine. So the recording then should be in good quality. Okay, so yeah, model. Model is the second component. First component is data in machine learning. So we have a bunch of data points in a CSV file, like temperature recordings or daily weather measurements from earlier days. And we have downloaded for you such measurements and stored in a CSV file on our GitHub repository for our school. So you will get the link to this file, and you will then try yourself to read in these data points. However, you could also get the data yourself directly. Just want to point out to you, we have a really amazing data source for weather data, which is the Finnish Meteorological Institute. So, and if you Google FMI get observations, you can download observations at all possible weather stations in all around Finland. I think back till the last 100 years. Oh, no, so the daily measurements are available since 2010, high resolution, and others are back till 1960s. So not 100 years. That was too much promised, but at least till the 1960s, you could download the weather measurements freely from FMI, from the Finnish Meteorological Institute. However, we did this already for you. And also one of our teachers, I think Dr. Yutian, has prepared a Python script that we might share that allows you to scrape this data. So you don't have to go to this user interface, but you can, in Python code, say, I want to download all weather measurements between this time and that time in a rectangular region specified by GPS coordinates, which is pretty. Okay, but for the exercises themselves, we have already downloaded this data for you. So it's on this GitHub repository, and the link to this GitHub or to this CSV file you will find in these notebooks, in the exercise notebooks. Okay, so let me continue with exercise 1. So we have data from our CSV file that we got from the Finnish Meteorological Institute. Now we choose a linear model. So the next question is then, how do we learn the best hypothesis? How do we train the model? Which hypothesis or model parameter? Yeah, by the way, each hypothesis here is fully characterized by the weights. So we could denote this by a superscript W. So each hypothesis is fully identified by the weights. So instead of searching over the hypothesis instead of searching over the space of linear maps, we will search over the space of weight vectors. And this is somewhat nicer. But now the question is, how do we compare the quality of different choices for weight vectors or different choices for the hypothesis? So here, this predicted label is obtained by applying the hypothesis with some given weights to the ith data point or to the features of the ith data point. And a very natural choice for quality measure is the squared error loss. So we look at a data point for which we know the label. So for example, in FMI data from previous days, we know what has been the maximum daytime temperature in hindsight. And we can compare it to the prediction that we get from applying a certain linear function. And then we get a prediction error. And we take the square. This is then the squared error loss. And we sum those squared errors up for all data points that we have in our training set. So we assume we typically have more than one data point for which we know the labels. Okay, and now empirical risk minimization is just a principled way to learn or to minimize this loss. Because per se, it's not clear why should we minimize the average of the squared errors. So ideally, I would like to minimize the squared error, the squared prediction error for all data points. I want to have a predictor that makes minimum prediction error for every data point, for any data point. But this informal requirement is a bit difficult to achieve, because what does it mean for any data point? It's typically not a good idea to learn a hypothesis that perfectly predicts all data points in the training set, because something might happen that is called overfitting. So we need some way to formalize the notion of any data point. And one way to formalize it is to assume that the data points are realizations of random variables drawn from some probability distribution, like a Gaussian distribution. And once we know this probability distribution, we can say we want to find a hypothesis that has minimum squared error in expectation, or whose mean squared error is minimum. Sounds like a good plan, but on the other hand, we don't know this distribution. So what do? We estimate this distribution and estimate the expected error by using a sample average, or the average loss over all data points in the training set. So this is a sample average. And we hope that this sample average is a good approximation of the expectation of this squared error. And this is not always the case. So a key problem in machine learning is to find out conditions, or when does your model and your data set allow that this sum is a good approximation of the expected squared error loss. This is one of the hardest problems or challenges in making good use of machine learning, but we will not dig into more detail here within this school. We assume we have enough data, so minimizing the sum of squared losses is a good idea. Okay, so what we end up with is an optimization problem. So we want to find the weight vector of a linear hypothesis, of a linear map, such that the average squared error loss is minimal. So this is just a formal spelling out of the principle of empirical risk minimization. So we want to solve this optimization problem. Okay, how do we do it? So how can we solve this optimization problem? Well, it turns out that the objective function of this optimization problem, so we can write this as an optimization problem with an objective function f of w, which looks like this. So you can stack the feature vectors of the data points into a matrix. So you can stack these individual feature vectors into a matrix, which we call feature matrix. So the feature matrix here. And this has the features or the transposed feature vectors as its rows. So the first row has the first feature vector, the second row has the second feature vector, and so on and so forth. Yeah, by the way, what do you think, which Python type or which Python object do we use to represent such a feature matrix? So we assume that the features are numbers. So we have a regular arrangement of numbers. Yes, a NumPy array. So this is exactly where NumPy's array come in to represent this feature matrix and this label vector. So we also stack the labels of individual data points into a NumPy array. So this becomes, the feature matrix becomes a NumPy array, and the labels stacked together become a NumPy array. And then we can write this objective function in a very compact form as the squared Euclidean norm of this difference. So we try to approximate the label vector using the matrix vector product given by the feature matrix times the weight vector. Okay, and it turns out that this function, this objective function, is a nice function. So this objective function is what we call smooth. So we can take derivatives, and the derivatives don't change too rapidly. Then it's called smooth, and it's convex. So it's like bowl-shaped, or the segment of 2 points on the graph are always is always above the graph of the function. So then it's called convex, and such a smooth and convex function can be minimized iteratively or optimized iteratively using gradient descent steps. So the idea of gradient descent is you start with some initial guess for the optimal weight vector that minimizes the training error. Let's say it's all zeros, or you initialize. Yeah, in the exercise we will initialize these weight vectors with all zeros, but you could also initialize maybe using some other optimization method, approximate optimization method. This would be called a warm start. Okay, so but given such an initial guess, we try to improve it. We try to improve it by moving in the opposite direction of the gradient, because moving in the opposite direction of the gradient typically reduces the function value, because we go down the gradient. You go down the function, so you should reduce it. Of course, this is not always true. If you would go too far down the gradient, like here, and we would extend here the objective function. So if we would move here with a large step size, we would actually increase the function value. So might not always be true, but if it's sufficiently small, if the step size or learning rate alpha here is sufficiently small, we are guaranteed that we will decrease the function value. Yeah, this also brings me to this effect of the learning rate. So this alpha here, or which measures the amount of the length of the step, the amount of traveling we do down the gradient is called step size or learning rate alpha. This is an important parameter. So in the exercises, you are asked to play around, try out different values for alpha, and observe what happens to the overall algorithm. In particular, if alpha is too small, then you make too little progress. In the extreme case, if you set alpha 0, then you make no progress at all. You always stay where you are. There's no progress. There's no learning happening. That's why also alpha is sometimes called learning rate. So you must make alpha a bit larger than 0. But if you make it too large, it might happen what I sketched before. You might actually increase the function value. So you might diverge. The iterates that you get from the gradient descent iterations might diverge. You might increase more and more the function value, and you might increase it fast. So a typical indicator for this is when you have some overflow or numeric overflow problem in your implementation in Python. when the values become like 10 to the power of 10, the objective value. This is an indicator that your step size has been chosen too large. Yeah, but let me stress again, choosing optimal alpha is far from trivial. So many research papers study ways to find out what could be a good choice for alpha given a certain data set. Okay, but if you know something about your function, like if you know that the gradients of this objective function, they are Lipschitz continuous, so they do not vary too much. So when you look at the gradient at two different locations of your objective function, so you look at your objective function, here you have a gradient here, and you have a gradient here. Then the change in the gradient must be able to we must be able to control it in terms of the difference between the arguments. So here is the difference, the norm of the difference in the arguments, and this norm of the difference in the arguments must provide a bound, must provide an upper bound on the difference in the gradients. So here we have the gradient at FW. And here we have the gradient at FW prime. And this change in the gradients should not be too extreme or too high, too rapid. That's we call also, that's a smoothness condition. And whenever you know such a smoothness condition, or you know that your objective function satisfies the smoothness condition, and you know the constant beta, typically the smaller beta you know, the better. But it's typically hard to get such an upper bound, or to ensure such an upper bound, to be sure about such an upper bound with a small beta. But if you have it, then you have a particular choice for the step size, which is 1 over this beta. And then for this step size, you are guaranteed that the gradient steps converge. And this is the proofs of this are basically an exercise for anybody studying convex optimization. So this is not too hard to walk through step by step. Okay. So one challenge in using gradient descent is choice of alpha, which we now discussed. Another challenge is, how do you compute this gradient efficiently? In order to do the gradient step, you need to compute the gradient, and you need to be able to compute the gradient at different locations, because the locations where you evaluate the gradient changes as the iterations progress, because this WR is the weight vector after the rth iteration. So this changes from iteration to iteration typically. So you need to be able to evaluate gradients at different locations. And this is sometimes not trivial. Does anybody of you know one algorithm that is very useful for deep learning models that is able to compute such gradients efficiently? One very popular or famous password algorithm that is used to compute the gradients of the loss function when you have deep neural networks. Yes, BP. What does BP stand for? Belief propagation. Backpropagation. Yes, that's what backpropagation does. Backpropagation is a message passing algorithm in a certain sense for computing the gradient. Just to mention, this gradient consists of individual partial gradients. So one partial gradient for each entry of this weight vector. And if you have many weights, like a weight vector with billions of weights, like you have nowadays in large deep neural networks, you have to compute such a gradient, which is a vector with billions of entries. So a lot of computation. So be sure that you are able to compute this gradient efficiently. And backpropagation is one way to do this efficiently. However, we only consider linear models to train ourselves in federated learning. And here we can come up with a closed form expression for the gradient. So it looks like this. You can verify this expression using the calculus described in Appendix 4 of the Convex Optimization book by Boyd and Vandenberge. This book is available for free online. So there you can find all the calculus tricks, calculus rules to come up with this formula. for the gradient of this function. Okay. Yes, and so we have already our algorithm for linear regression. We have already a learning algorithm, an iterative learning algorithm, which is gradient descent for linear regression. So what do? We start with an initial guess for the weight vector, and we repeat these updates, these gradient descent steps for a sufficient number of times. And here I've also shown a snippet, code snippet, that you also find in the notebook for exercise 1 that implements this gradient step. Okay, so we are aware of the challenges in choosing alpha, the step size. We now know how to compute the gradient for linear regression. But then there's also a third question that is challenging for the implementation. When to stop? How many of these iterations should we do? And there is no, I'm not aware of a universally applicable good answer. There are different options depending on the domain knowledge that you have. So if you know, for example, such an upper bound on your objective function, if you know such an upper bound, then you can derive a required number of iterations to achieve a certain suboptimality. So you can derive the number of iterations required to get within, let's say, epsilon, an epsilon band of your optimal function value. So you can derive how many iterations do you need. But these bounds or this theoretical number of iterations, they depend on the validity of this inequality. So you must be sure that the objective function that you optimize satisfies this condition. And you must know the beta here. The challenge here is, so sometimes this might be possible. However, remember that this objective function, f of w, is defined via label values and feature vectors of data points. And what makes optimization more delicate in machine learning is that you typically have not much control over the feature vectors. You must take whatever comes in there, whatever the FMI weather station provides you for weather measurements, you take as features. So you have not that much control over the feature vectors and the labels of data points. So this might be not too useful. However, there are certain ways to kind of nudge the objective function into something that satisfies this condition. For example, feature standardization. You can prove that if you normalize the feature vectors to have norm 1, so you actively distort or modify the feature vectors, then you can ensure such an upper bound using a determined number beta. Okay. Yes, another option would be to monitor the decrease. So to continue these iterations until there is not much progress, until the function value doesn't drop too much from one iteration to the next. And the third option might be, well, in the end, what I'm interested in is not so much to solve this training problem. My ultimate goal is not to solve this optimization problem. My ultimate goal in machine learning is, or in many machine learning applications, just I want to find a good choice for the weight vectors. I want to find a good choice for the weight vectors. And one way to measure the quality of weight vectors after training is trying out on a validation set. So you do these updates for the weight vectors and you basically ignore the function values. This is just a training error. You ignore the function values, but after each iteration, you try out the new weight vector on a validation set. And you just look at the validation error and see if this validation error is dropping enough or is reduced by a sufficiently large amount. You could continue going. Otherwise, if there's not much progress or not much reduction in the validation error, then you stop. And this is sometimes called early stopping. This is, I would say, one of the standard ways to decide the number of iterations when you train a neural network, for example, using Keras library. You don't look at the decrease in the actual objective function, which is the training error, but you look at some other error, or the validation error. Okay, yeah, here I plot a few iterations of gradient descent. This you find also in the notebook, in the exercise 1 notebook, so you can run it yourself. The code that generates this figure. In this figure, you see a few data points. Each data point is characterized by a feature x1 and a label value. And I also indicate 3 lines. Each line indicates or represents the linear map. Remember, we learned the weight vectors that we use for a linear map. So this here is a linear map that we get using the weight vector in the first iteration. So this is a linear map obtained using the weight vector in the first iteration, which is initialized to something. In this case, it is initialized to all 0. So that's why this first line is flat, because the initialization for W is all 0. Then we do the first gradient descent step, and we find already a beta weight vector. So this is a linear map using weight vector W1 obtained after 1 iteration. Then we do another step of gradient descent, and we get the green curve. So this is the linear predictor using the weight vector obtained after 2 iterations of gradient descent. And you see, we already have, after 2 iterations, we have already a quite reasonable linear predictor. Okay. Yes, just to point out, this will not be covered in any depth in the exercises and in the school. But then when you really want to use these methods that I now provide you and that are contained in the notebooks, always validate the predictor that you learn. So you in this notebook, you just are focused on finding the weights of a linear map that has a small training error, but you should always validate the resulting linear map on a validation set, which is kept aside and not used for training the model. However, exercise 1 per se only looks at the training process using gradient descent. Okay, so now I come to the overview of the exercise tasks. So each exercise has tasks in the end, task descriptions. So the first task in exercise 1 will be to generate synthetic data. You have to generate synthetic data using Gaussian random vectors, so or Gaussian random variables. Each data point has a feature vector consisting of 2 features. The first feature is drawn from a standard normal distribution, and the second feature is always 1. Why not? We use a feature that is always 1. We can do it. Why shouldn't we? And then you generate the label. You generate the label of a data point using this linear combination of features using some randomly generated or arbitrary fixed numbers for the weights W1 bar and W2 bar. So these are kind of the true weight vectors. And generating the data like this allows us to measure the error or the quality of gradient descent, because we know what the true values are. So we can compare the weight vectors that we obtain after a different number of gradient descent steps with the true value. So we can compute the estimation error. And here this task asks you to try out different choices for the noise. So we add also noise to the labels. There's some intrinsic noise using a variable strength. Sigma is a noise strength parameter. And you should then look at the quality of the weight vectors that you get after a certain number n of gradient descent steps as a function of the number of gradient descent steps, of the noise strength, and of the number of data points. So M is the number of data points that we use in our data set to do linear regression or to apply gradient descent to linear regression. Okay, and task 1, the second task in exercise 1 is then, after you got familiar with gradient descent for linear regression on toy data, apply to some real world data. Like real world data as we provide here in the CSV file on our GitHub repository. So you find the link here and also in the exercise 1 notebook. So we then ask you, learn a linear predictor, a linear hypothesis for the maximum daytime temperature based on the minimum daytime temperature at some place in Finland. We don't know where, at any place in Finland. And to do this, we use previous weather measurements, daily weather measurements that are stored in the CSV file. Okay, I now suggest after I have explained exercise 1 and I start discussing exercise 2, let's have a 5-minute break. And I'm also happy to take questions on the chat. Yes, one of you pointed out already some problems with the notebook. I might need to update it, so I'm permanently push the draft version. I will look at this after my lecture. For Alto students, I would like to have this course graded with a numeric grade 1 to 5. Yeah, and if you observe problems with executing the notebooks, please post your comments and questions and answers also on the Slack channel for this exercise. So if you have now observed some problems with exercise 1, please post those in Slack channel exercise 1, so that other students can also follow the discussion.
Yəni ağır zatdır ha, yəni bu cür rahat deyəndə təqsimləndirir. İndi sən məsələn daha dəng olursan mənim kompüterə, mənim kompüterim bərabər də nə qədər CPU-su var, nə qədər.
Yes, hello, back to the first lecture. Now, seasonal school, I got some questions on the chat. There are some problems with the exercise 1 notebook. I will try to polish it and correct it by today and push it again. However, I think these are only minor issues that you should be able to work around based on the comments you see on the Slack channel. Then there's another question: how can we have access to the slides? I will post the slides on the school site. So I have linked them already there. Let me show you quickly. Desktop. So I will always put the latest version of the slides on our school site, and here you can find them here on the school site. Also, I will ask them material from the other lecturers to post on the school site. Okay, then there was more question. You mentioned data standardization. Are there any negative effects of applying it in terms of preserving the information contents of a data set? That's a very good question. So in general, you will not lose information when you standardize the data, because the normalization is typically an invertible transformation. Like you divide each feature by a non-negative number, which is the variance or the sample variance of the feature. So you always, data normalization and standardization is typically an invertible transformation. So by applying something invertible, you cannot lose information. So you will not be able to lose information. However, it might be that the standardization you do is based on a training set which has different characteristics, statistical characteristics, or slightly different than the validation set. This might be called concept drift sometimes, or non-stationary data, and then it might not have the effect that you would hope for, like speeding up convergence of iterative methods. But in general, it's not too risky. I would say it's not too risky to do normalization, so it would be worth a try. Okay. Any other questions? Let me have a look at the chat. Slides can be accessed via the site. What are the deadlines for each exercise? There are no formal deadlines. So whenever you want a grade for the Alto course, you are free to submit. The course runs officially till June. So you have a lot of time to work on the exercises. So there are no deadlines for the exercises. However, we provide the support, and this is quite some investment, and I'm very glad that I got the confirmation from our teachers. They might help you only during this week. So this is, of course, quite some resource intensive, and you get support on the Slack discussion forum mostly during this week. So if you work through the exercises this week, then you might get more support than the following weeks. I cannot promise you 24/7 support beyond the week, and also not during this week, of course, because we're all volunteers. But for those students who want to get credits as a university course, like at Aalto or any other university in Finland, you can transfer the credits within Finland at least. You must submit it when you want to have the grade. Okay, then there was one question regarding the Docker container, which I cannot really help. I'm not an expert on Docker. Please post this question also on the Slack channel. I hope we have some experts on Docker. At least I know some of the teachers know about Docker. Okay. Yeah, feel free to post any other questions on the chat, and I will try to cover them at least during the breaks between the sections or the exercises that I discuss now. Okay. So let's continue with exercise 2. So exercise 1 was basically the basics, or discuss the basic machine learning method that learns a linear map by fitting it to a bunch of data points. And now we introduce some more structure to the data, or we take into account a network structure of the data. Already in this Finnish Meteorological Institute data, in this weather data, we have a network structure because FMI stations are distributed over Finland. And so you could, we obtain a network structure in the sense that the weather measurements of stations that are nearby are typically have similar statistical properties. So I'm not an expert on meteorology, but I assume, and you might hear more about this in the lecture by Dr. Schicka on, I think on Wednesday. But when you have weather stations, for example, along the coast, then the statistical properties of the weather observations might be more similar than between those stations and the station in Lapland in the north, more near the Arctic. So you could say stations that are nearby are similar or have similar, the data at those stations or generated by those stations are similar. And we encode this similarity network structure by what I call an empirical graph. So this is our main mathematical abstraction. That's the most difficult mathematical concept here in this whole school, an empirical graph. So what is an empirical graph? It's an undirected graph. So the nodes of this undirected graph represent data sets. For example, the data generated by weather station, by some weather station in Kamppi or in Kaisaniemi. So each node represents a different weather station and the data set generated by this weather station. So we will see in a second how to attach data and models to the nodes. And this is, yeah, what I forgot to mention, this exercise 2 will be mainly based on methods of this Network X library, which is a really cool tool to work with network data and network models. Because what I find still amazing, you can attach to the nodes of a Network X graph of such an object, a Python object that represents a network. You can attach basically anything to a node. You can attach to it a movie, a CSV file, a model, a deep neural network, a PyTorch model. You can attach really to each node. This is amazing. Find it still amazing. Okay, so, but first of all, such an empirical graph is represented by a network X graph. So here I show a code snippet that generates such a network, undirected network using nx.graph. And then we add nodes. So we first build up the graph. So we start with an empty graph. This line here generates an empty graph, and then we add nodes. So we add nodes, one node for each station. So this num stations variable might be somewhere obtained from a code that counts how many different weather stations, or from how many different weather stations do we have data in our CSV file. So this number of stations is the number of weather stations that we have in our data set. And then we add edges. And then Dr. Yu Tian has prepared us a nice code, a ready-made code that connects each weather station with its 4 nearest neighbors. So this 4 is a parameter you can change. You can also generate a weather network or FMI network with each weather station connecting to 3 nearest neighbors. Would be interesting to study the effect. And we not only have edges between nearby or similar weather stations with similar data, but we also quantify the similarity. So we have some edge weights that quantify the similarity. How could we, what would be a reasonable approach to come up with similarity measures between weather stations? So let's look at these weather stations. How could we quantify the similarity between 2 weather stations? Yes, we could use the distance between stations. We could say we compute the distance, we take the GPS coordinates and compute the Euclidean norm or the 1 norm or whatever norm you want, and use this as an inverse measure. So the larger the distance, the smaller the similarity. So we could, for example, use the distance and plug it into the exponent of the negative exponent of an exponential function. So this would be like a kernel method. Does anyone else of you have an idea for how to find out the similarity between FMI stations? and a notion of similarity that is more geared towards the data. Yes, a very good comment. Compute the correlation coefficients between data sets, or something, a measure of statistical similarity. So what is a most general way to measure similarity between, or statistical similarity between two data sets? Correlation, I heard already. Cosine similarity, if you can represent data sets by vectors. But what if the data set is something like this here? It's like a few lines in a CSV file of weather measurements. So we just have a bunch of data points. Density distributions. We could look at how similar are the probability distributions or histograms of the data sets and use those. By the way, does any one of you know a recent paper that constructs similarity graphs like this? I would be interested in this, because this is exactly what we are currently working on methods that learn such a similarity graph by looking at statistical similarities. Okay, but within this school, we consider very simple approaches to find these edges, like connect each weather stations to the 4 nearest neighbors and use the same edge weight. But there are many, many possibilities to make this more advanced, this approach. Okay, and now comes the data. So this is what I mentioned with this network X objects and network X methods in Python. You attach to each node. So this here, GFMI node I is the ith node in this graph, and you just define a new feature or a new attribute. It's called node attribute X, and store a whole feature matrix there. So you have individual data points. So this here is one data set, one single data set that we considered before, and each node has a separate data set, has a separate number of weather measurements, but only for this location, of course. And we attach it to each node in the network X graph. We attach also the labels. So using these 2 lines of code, you generate a network data set, in a sense. You have a network. So first you generated a network as a network X graph, and now you attach feature matrix and label vector to each node. And those are different. So each node holds a different feature matrix and a different label vector. Okay, next step, data. We also want a model. Machine learning has data, a model. We also need a model. So we define a separate model for each node. So this line here attaches a weight vector for a linear model to each node, and it initializes it with 0 to start with. Okay, so now we have a separate machine learning problem at each node. So we have a whole network of machine learning problems. This is sometimes called a multitask problem or multitask learning. And this is really beautifully stored and manipulated in a network X graph, because you can attach so many different things and powerful things to the nodes of a network X graph. This is just a weight vector. We could also attach to a node a whole PyTorch model with 100-layer deep neural network. It might be a bit slower then, of course. Okay, so to start with, to warm up, we don't take full use of this network. Yeah, I might ask all of you, please mute your microphones. I was thinking that I muted it by default, but it seems my Zoom skills can still be improved. Okay, so as a warm-up, we learn a single model for all data points, for all local data sets. In principle, we would have the power, we would have the ability now to learn different models for each node, for each weather station. But this we do in exercise 3, in the next exercise. In exercise 2, we are just a bit more humble and start to warm up with learning a single global model. So all weight vectors at all nodes are the same. We learn one single model for predicting maximum daytime temperature from minimum daytime temperature. What could we do? Well, we could just ignore the network structure and pool together all local data sets. This is what we actually did and what you will do in exercise 1. You will have this CSV file, one big CSV file, which has been obtained by pooling together using some lines of Python prepared by you, pulls together all the observations from all the weather stations. So we could do this. Do you think this is a good idea to pool together all local data sets? What could be a problem? This is already where federated learning comes in. Why don't we want to share raw local data? We could share local data. Yeah, so storage capacity. We might have not the central server might not have enough memory to store all the local data sets. Very good point. Privacy. We might not want, I mean, here it's weather. Weather is rather harmless, but still you might not want to share your identity if you have a local weather station. Because if you share your local weather recordings, then they might have a unique signature, so they can spot you. This weather is from you. So what we would rather share are some statistics like averages or gradients. And this we will see now. We will see instead of sharing the local data sets, we can, without any sacrifice in accuracy, in learning accuracy, implement gradient descent to learn a single global model only by having the FMI stations sharing averages or gradients instead of raw data. So how does it look like? Well, you just plug in this stacked feature matrix and do simple linear algebra or manipulation of the expressions, and what you get, you can write down the gradient step like this. So the gradient update is a sum of terms, which I call local gradients. And these local gradients do not contain directly the raw data, but in this matrix multiplication, somewhat hidden, is an averaging step. So here, these gradients are averages over local data sets. So we share averages. And this is somewhat similar to like statistic institutes, like Finland of Statistics makes studies or makes surveys. What is the income of persons? So, and when you have a group of people like all professors at Aalto Department of Computer Science, and you would publish the average salary, then this is somewhat privacy preserving. But if you would publish the histogram or individual salaries, then this could be used to spot this guy, this Alex Jung, earns this much individually. But if you publish only average salaries, then you are somewhat unprotected somehow by those earning less or earning more than me. And this is exactly what is happening here. These local gradients are averages. So they provide already some privacy protection. Okay, and then the only question is, how do we compute this sum here, the sum of local gradients? And the most direct approach, or maybe the simplest version of federated learning algorithm is as follows. So you start with some initialization for all weight vectors at all nodes, like everything 0. Each node computes then the gradient, the local gradient, using his or her local data set, and submits or sends these local gradients to some central server. The central server then implements this update step, and the update step results in a new weight vector, and this weight vector is then broadcasted to all local data sets or all nodes again, because they need this new weight vector to evaluate the new local gradients. The local gradient always requires the current estimate, the gradient descent estimate. That's why we need to broadcast back the result of the gradient descent step, such that in the next iteration, the nodes can compute the correct local gradients. And they come already, in practice, this is not so easy because there might be link failures. So some nodes might not get the most current iterate, so they might use some outdated weight vector, like in the 2 iterations before, and evaluate the gradient using this old weight vector. So the gradient is also wrong. So what happens in this outdated information? And there are many papers looking at these scenarios and trying to analyze how much outdated information can we tolerate in this simpler approach. Okay. However, we will not follow this approach. In exercise 2, you will see another approach, which is fully distributed. So here, in this approach, we need a central kind of management unit, or some central unit that orchestrates the whole thing, that collects the local gradients, does the gradient descent step, and broadcasts back the new weight vectors. And now in exercise 2, you will see how to do this in a different way, which is fully distributed. So there is no central unit. This is fully distributed, decentralized. And the idea is to compute this average of the local gradients. So this term here that we need for the gradient step, this average of local gradients, using a network averaging algorithm. And this network averaging algorithm, they follow a very intuitive message passing rule. So in each iteration, so they are itself iterative. So in each iteration, each node updates his or her information or local property, which I call G at node I. G at node I is the previous local information times some weight plus all the neighboring local informations with some weights. So we combine the local information, which is this G superscript I, and all the local informations at the neighbors, but these are weighted by some weights. And it turns out there are reasonable choices for these weights. Like one of them is called Metropolis Hastings weights, such that when you repeat these updates, these local updates or message passing updates sufficiently often, then these local attributes converge to the average of the initial values. So, and the idea is now simple: start with the initial values being this local gradients. So these here are used to initialize the network averaging algorithm. And then we run a sufficient number of iterations of this network averaging algorithm. And it turns out after this number of iterations, each node has as its local updated attribute this average. So this is what this convergence result is telling us. If you repeat this network averaging steps sufficiently often, this GI at each node will be the average of the initial ones, the average over all network nodes. So over all nodes in the network, we average the initial private values or local values. And these initial values are these gradients, local gradients. So what you have in the end is this average. And after you have the average at each node, you can do the gradient step. So we have our first distributed federated learning algorithm here. Algorithm 1 in exercise 2. And note that you have here two loops. So we have an outer loop that repeats the gradient descent steps. And in each gradient descent step, for each gradient descent step where we compute we must compute this average. So we must then have an inner loop where we iterate the network averaging algorithm. So we have two nested loops, an outer loop, which repeats the gradient descent steps, and an inner loop, which repeats the network averaging steps or updates. Okay. So the tasks for exercise 2 will be try out algorithm 1 for a toy network data set that is already generated by the starter code. This toy network consists of two different clusters. So you should see that these weights, they become constant over each cluster of these two clusters. And then you should study the effect of adding one single edge between clusters. And you will see that this network averaging breaks, because you want, the overall goal is to learn a single global model. And as soon as the network is connected, you learn the same model for all nodes in every connected component. And if you have two clusters, even if they share one single edge, this whole thing becomes a single connected graph, and you learn the same model. And we will see then in exercise 3 how a different approach, which is based on regularization, is more graceful to having a bit of connection between clusters. So even if you have a tiny connection or weak connection between clusters, you will learn approximately the same model for all nodes in the clusters, but they might be different. Different for different clusters. Okay, and yeah, the second task in exercise 2 is to learn a model in a distributed way using algorithm 1 to predict the maximum daytime temperature from the minimum daytime temperature using all the data that you have in a CSV file, which is obtained from the Finnish Meteorological Institute. Okay, so let's now have again a short 5-minute break, and I will try to answer some questions before we discuss the last exercise, exercise 3. So there was one question. Can the local gradients be from mini batches? So here, I think here, yeah, here, this local gradients, yeah, this would be a full gradient step or full gradient. This can also be replaced by, so this xi, this feature matrix might be obtained from a subset of all data points. So you might use here batches, mini batches for computing these gradients. Yes. There's another question. In the exercises, we have considered the loss function is differentiable to apply iterative algorithm. What happens when the function is fully differentiable? I assume you mean if it's not differentiable. Not fully differentiable. Yes, if it's not fully differentiable, yeah, this is beyond the scope of this course, unfortunately. But there are powerful methods, and actually our research studies this, which are based on proximal algorithms. Some of them are called primal dual methods, and they extend this gradient methods that we have here to functions that are structured but might not be differentiable. So in particular, when you have sums of convex functions, then you can minimize them efficiently, even if some of the components of the convex functions are not differentiable. But this is beyond the scope of this school. Yeah, one very popular is ADMM, alternating direction method of multipliers. This method can be applied to convex optimization problems involving non-differentiable functions or non-smooth functions. Another option, yeah, a simpler option would be to use sub-gradient descent. This can also be applied to convex but non-smooth functions, sub-gradient descent. But again, this is beyond the scope of this school. But another question, what are the possibilities to use network X for testing federated learning algorithms for data sets like MNIST? I have no experience with that. So I didn't see network X implementations for this federated MNIST experiments. That would be interesting to see, but I didn't see something like this yet, so I cannot answer this question. Another question, what is a typical ratio of update between the network averaging to new local gradient? Are there multiple network average iterations per local grade? Are there multiple network average iterations per local gradient update? Yes, this is something you should try out. So in the first task of exercise 2, you should try out using different number of inner iterations and outer iterations. Typically, you need more than one iteration of network averaging during each gradient descent step. So let's say you use 10 gradient descent steps, and within each gradient descent step, you must use, let's say, 10 averaging iterations, network averaging iterations. It's typically not enough to use only one iteration. We will then see in exercise 3 that there's no, the algorithm we discussed there has no distinction between outer and inner loop. There's only one loop, which is a gradient descent step. But in this simple algorithm 1, you need more inner iterations during each outer iteration. And the number of inner iterations, the number of how often you need to do this message passing in the network averaging, this depends on the convergence speed. And this is also not far from trivial to have a precise bound or characterization of the number of iterations, number of network averaging iterations required to achieve a certain quality of consensus, so that all local vectors here are within a small error of the average. So this is also not trivial. And you typically need to assume some knowledge about the network structure, like in the form of eigenvalues of matrices that are assigned to network structure. And you will have tomorrow the lecture about spectrograph theory. We'll talk about such characterizations of network structure via matrices, and in particular via the spectrum, via the eigenvalue distribution of matrices that are assigned to networks. Yeah, but in general, yeah, just the point here is you need typically more than one iteration of network averaging. Yeah, there's another question. What about mirror descent? Is it related to this proximal methods you mentioned? Yes, mirror descent is one special case, one instance of a proximal method. So let me then continue with the last part of this lecture today, which is about exercise 3. So in exercise 3, we give up the requirement that each node has to have the same weight vector. We don't want to learn a single global model, but we really want to do now network federated learning. So we want to learn a potentially different model, different weight vectors for each node. So we want to learn for each weather station a different predictor. And this might also be called a personalized model. We want a different model for Tampere than for Turku, because the weather statistics might be different between Tampere, which is inside the land, compared to Turku, which is on the coastline. You might not find a single weight vector that does equally well in Tampere or in Turku. So you want to learn different weight vectors. However, so what we could do is, in principle, we could learn a separate model for each local data set. So we collect the weather measurements for Tampere, we collect the weather measurements for Turku, and learn completely, ignore the existence of the other problem, and learn a model for Turku and learn a model for Tampere. So why might this not be the optimal way to go? If we have enough data at each node, so if these nodes are data rich, then it might be the best way. So just independently learn models for each node based on the local data set. However, these local data sets might be small. And if these local data sets are small, you might run into overfitting easily. So what you would like to do is you want to pool local data sets that are statistically similar. You want to pool them together to get larger training sets. The more training data points you have, in general, the better. So you want to pool them. And equivalently, this means that we want to learn weight vectors that are similar or close by each other for all nodes that are in a well-connected subset or cluster. So we want to learn the same model. We want to learn the same model parameters for all local data sets that are statistically similar, which means if we have a reasonable network structure, all these data sets form a well-connected cluster of nodes. So we want to force the weight vectors of well-connected nodes to be similar. And so this is a form of clustering assumption. And this clustering assumption we can implement. One way to implement it is by requiring a small total variation. So this total variation is defined as the sum over all edges. So this summation goes over all edges, undirected edges, but weighted with weight Aij. And we sum the differences in the weight vectors of the nodes in this edge, on this edge, or adjacent to this edge. So we pick each edge, we look at the weight vector here at one end, the weight vector at the other end, we compute the squared Euclidean norm of the difference and multiply it by the weight of the edge. And we sum this up over all edges in the network. And it turns out if you require this to be small, essentially means that the weight vectors can only change over a few edges with small weight, or equivalently, the weight vectors must be constant over nodes that are well connected with each other with large weights. So here we have it, the ultimate machine learning problem or federated learning problem, which is a regularized form of linear regression. So we want to find weight vectors. We want to find the weight vectors at each node. So here the optimization is over a collection of weight vectors. It's not only one weight vector, it's a collection of all weight vectors that are assigned to the nodes in our networked data. And we want to minimize the sum of two components. The first component is the training error here. So this is the standard training error that we got from, from using squared error norm and linear models in linear regression. It's the training error. And then there's a second component that measures the clusteredness. So this is the total variation. And these two are blended by using, the blending is controlled by a parameter, which is called a regularization parameter, lambda. I used lambda subscript TV because when you use it then in Python, lambda is you should not use lambda as a name for variables. Lambda is kind of a keyword in Python. That's why I used lambda underscore TV. And this lambda controls, or this regularization parameter controls our preference. Do we want more clusteredness? So when we make lambda larger and larger, and this you will try out in exercise 3, making it larger and larger results in the solutions of this optimization problem to be more and more constant. And at some critical point of lambda, so let's say lambda is 10,000, what you get, the solutions of this optimization problem are perfectly constant over all nodes in connected components. So if your network is connected, so there's a path between each two nodes, no matter how the cluster structure is, you will get a constant weight vector for all nodes. And this is the special case that we have observed before. So before, we wanted to learn a global model where all local weight vectors are the same. And you can achieve this. So this here is a special case of this new algorithm or new learning problem that you obtain when you choose lambda large enough. So you re-obtain the previous setting of learning a single global model by using lambda large enough. However, we're now interested in a more intermediate regime of values, such that we learn different weight vectors for different clusters. So we would like to have one weight vector that is learned for all nodes in this cluster, in this toy example, and another weight vector that is learned for all nodes in this cluster. And they might be typically different because the data sets are different. The data has different statistical properties in this cluster. So this cluster might be weather stations in Lapland, for example. And this cluster might be weather stations on the southwest coast of Finland. So you want to have different weight vectors or different predictive models for these different clusters. Okay, so now we end up with our optimization problem. So a machine learning problem typically means an optimization problem. How can we solve this optimization problem? Well, as you can verify more or less easily, this is again a smooth convex function. So we minimize it using gradient descent. And you can also get again closed form expressions for the gradient. So this here is essentially the gradient. This is the gradient. And when you look at it, it looks like a message passing rule. So at each iteration, each gradient descent step amounts to updating the current weight vector that we have at node I using the previous iteration or the previous weight vector at node I, and only terms that are connected by an edge, because these weights are only non-zero for two pairs of nodes that are connected by an edge. So you have to compute this update. This gradient step involves only local communication. So it's can be implemented as message passing. So you must read in the weight vectors of your neighbors to compute this term. So this term here needs the neighbors of the gradient step. And then there's a second term that only needs the local data set. So you only need local data set and the current weight vectors or iterates at the neighbors. So it's a local message passing update rule that we have here. And this is exactly what you will implement in exercise 3 as algorithm 2. So we have now algorithm 2, which is just repeat for a sufficient number of times this gradient descent steps as kind of over all nodes simultaneously. So you will iterate over all nodes in the network X graph. And for each node, you compute this gradient descent step. Yeah, and your tasks are then try out different choices for the number of iterations. The number of gradient descent steps depends on two things that I will discuss in a second. So you should try out the effect of using different number of gradient descent steps and also using different choice for this lambda. So when you choose this lambda very large, the resulting weights after a sufficient number of gradient descent steps, they should basically all be constant. However, when it's not too large, you should get weight vectors that are constant only on the clusters, but different between clusters. So this is a form of clustered federated learning. And you will hear more about clustered federated learning during the lectures on Thursday, I believe. Okay, yeah, and the second task is again, try out algorithm 1 on real world data, in this case, on the weather data from the Finnish Meteorological Institute. And we have provided some demo code or starter code that shows you how to read in this network of weather data from the Finnish Meteorological Institute. Okay, so that's basically it. That's basically it regarding the exercises. This was the overview of the 3 exercises that you are now welcome to work on and ask a lot of questions in the Slack chat forum. Yeah, I hope you enjoy the exercises and will get something out of it, learn something, learn by doing. Yes, just to build now the bridge to the next lecture, which is tomorrow. Tomorrow, the lecture will be about spectral graph theory. So it will be about matrices that are assigned to networks. And it turns out that this is useful for understanding algorithm 2, for analyzing algorithm 2, in particular to understand the convergence. Whenever you have an iterative algorithm, a key challenge is to find out when to stop. So how many iterations do you need? And to get an idea of how many iterations you need for algorithm 2, it might be useful to rewrite it as a linear system. So you can collect the terms here into a matrix Q and to a vector a lowercase q. And it turns out, for those of you, it's of course no news here, who worked already a bit with linear iterative solvers, such a linear iteration converges, or the speed of such a linear iteration depends heavily on the eigenvalue decomposition, distribution or eigenvalue spread, let's say, how much the eigenvalues of Q are spread out. So if they are very narrow, around one single value, extreme case would be the Q would be the identity matrix. Then all eigenvalues would be 1. So there would be 0 spread, which is the optimal case in some sense for such a linear iteration. But typically it's not so. So the eigenvalues of Q will be distributed. And how does Q look like? Well, if you do a bit of manipulation, if you massage these expressions, you come up with this expression for Q. So Q is a sum of two components. The first component is a quadratic form that is obtained by stacking all the feature matrices into a big block diagonal matrix. So this here, this depends on the local data sets. So this is the data term. And then there's a second component, which is the a slightly modified version of the graph Laplacian matrix. So this Laplacian matrix has on the main diagonal the degrees of each node, which is the number of neighbors. So that the first node here has degree 2. Yeah, it has 2 neighbors. The second node has degree 3. Yes, it has 3 neighbors. And then on the off diagonal, the Laplacian matrix carries the negative of the edge weights. And it turns out that this matrix Q contains the scaled Laplacian matrix of the network, of the data network. So this here depends on the network structure. And what is now the challenge here is how to control the eigenvalue spread of Q by, for example, data normalization. It turns out data normalization does something like controlling the eigenvalue spread of this term here, of this data term. But then there's also this other term, how to control the eigenvalue spread of the graph Laplacian. And this is then something you will hear about tomorrow. In particular, you will hear how this eigenvalue spread depends on the topology of a network. So roughly speaking, the best case would be if the graph is fully connected. So each 2 nodes are connected with each other, because then the eigenvalues of this Laplacian matrix, the non-zero eigenvalues, only non-zero eigenvalues are interesting. The zero eigenvalue is not interesting for the Laplacian matrix, believe me. The non-zero eigenvalues will be clustered very much for a fully connected graph. However, a fully connected graph might not be a good idea, because when you have a fully connected graph, you have to do this message passing over the maximum number of possible edges. So you would like to have a bit of a small or sparser graph. And this having a sparser graph means a sacrifice in the eigenvalue spread. So the eigenvalue spread will widen up for sparser graphs. But the more details you will hear about this eigenvalue spread in tomorrow's lecture about spectral graph theory. And yeah, the whole field of spectral graph theory studies methods to analyze and to control this eigenvalue spread. So it's far from trivial. Just I want to give you now a hint how this here connects to the next lecture tomorrow, which is by Professor Avrachenkov from INRIA. He's an expert on the spectral properties, on the eigenvalue spread of matrices that are assigned to networks. Okay, yeah, that's all from my side. I'm now happy to take your questions if there are something on the chat. Otherwise, don't hesitate to post questions and to answer questions or discuss questions of others on the Slack discussion forum. As I said, your active participation in the Slack channel will not be your disadvantage should you want to have a grade for this course. And yeah, I hope you enjoy the seasonal school, and I will now quickly look at the questions we have. Yes, so there's one question. The eigenvalue spread is the condition number. Yes, so one single quantity or one parameter that characterizes the eigenvalue spread of a matrix is the condition number. And you want the condition number to be close to the optimum, which is 1. Yes, one measure of eigenvalue spread is a condition number. Okay, that's all from my side. Thanks a lot for your attention and enjoy the school. Bye.